this presentation will be recorded. The names of people who listen to the webinar will not be a part of the recording. However, if you ask questions, you will then be part of the recording. So once again, welcome to this webinar. Today we're going to listen to Mitja Papinutti, who will talk about his work on dynamic analysis of floating bridges. So it's 1 minute past 10, so please, Mitja, go ahead.
Thank you, Matthias, for introduction. I'm very happy today to present my work and to show you some of the updates we did on dynamic analysis of floating bridges. I was here as a postdoc researcher where we did some interesting work on the topic of wind, and it all is actually a part of E39 project, where there have been launched a series of projects on how to cross and how to build the motorway in E39 in western Norway. And this brings some challenges due to the wide and deep fjords. And there have been several alternatives, as you see here, proposed for crossing of those fjords. Especially, there have been new technologies developed, new numerical models, and this is where I have been lately. Activity is in developing of numerical models. I was part of the group that has been before developed some of the implementation for the tension leg platform suspension bridge, and this concept was actually done as a feasibility study, and we show how these things can be possibly built and investigated. So before I start, I would like to have a few words about my past work. I started to work before this research about 4 to 5 years as a software implementer. We implement some of the hydrodynamic features inside of the commercial software Air and Bridge. At that time, we built an interface between two softwares so that we are able to calculate the hydrodynamic properties inside of the bridge software. And this was successfully done. And then the next project came where we implemented the wind buffeting analysis in time domain. And you'll see now that my research is actually going on this wind buffeting analysis and try to improve it in certain ways. Also parallel to that, I started my PhD at University of Ljubljana, where I will also later defend my thesis. During that time or after those projects, I was also involved as a consulting engineer in some of the floating bridge design, where my responsibility was actually working on a coupled environmental analysis, try to set up all the different softwares that we are working there and try to get some results that we're then able to use it for the actual design of the bridge. And this actually gave me motivation to do further work on the research. I noticed that there have been some possibilities to perhaps improve our formulation, and so we came up with the idea that we can introduce a self-excited force formulation for our projects. Actually, what is the background of my work is a analysis of response of the bridge. So this could be in general any floating bridge, any floating structure, but we have been recently focused on the TLP suspension bridge, where we have to add some additional interactions to what we know as state-of-the-art bridge equation of motions. In general, those bridges are nonlinear, so therefore they have to be described as a time-dependent damping and time-dependent stiffness. And as well, they have different load components, which are time-dependent, acceleration, velocity, or displacement. So you pretty much have everything on those bridges. And you need to kind of have a proper formulation where you can introduce those effects either on the left-hand side of the dynamic equation as an implicit, or you can put it as a nonlinear on the right-hand side where you iterate. So the background of this is that we use a Newmark implicit, explicit time integration scheme. And as such, this is then able to resolve these equations. So I go later on into detail what these different terms are meaning. But the first thing is I'm going to give you a short overview of the floating bridge equations of motions. And we're just going to go slowly through each interaction. We'll start with some current waves and hydrodynamics, and then we will move to the wind loads, where we'll have more focus. If we start first with the current loads, this has been already implemented in one of the softwares, and what we did here is we implemented the load formulation that is able to capture the current load distribution and also the movement of the structure. As you see here on the right picture, there are parts of the structures which are underwater, and those are exposed to the currents. As such, the currents are, you can say, more or less constant, so that would present a static load. But due to the movement of the structures, we have to have a formulation that calculates the relative velocity. So we are simply subtracting the stream and the element velocity, and then we are working with the relative velocity. This is in hydrodynamic theory also known as viscous drag damping, and those effects are of course present in the structure submerged under the water. We have solved this successfully, and in our numerical models usually there is one final element connecting bottom and the whole object, so that means we need to have a numerical accurate presentation of the current stream, which is nonlinear. And we achieve this by subdivision of the internal subdivision of the elements. The second thing that has been implemented is wave radiation damping and added mass. So to incorporate those effects in the dynamic equation of motion, we have to resolve them. These properties are frequency dependent. They are usually either measured in the water measurement objects or somehow numerically extracted. Those for this project were always numerically extracted with panel methods. So we build up an interface that is able to reproduce those forces. The challenge here, as you see on the right hand side, these are frequency dependent forces. For the hydrodynamic forces, they reflect as a added mass and added damping. What we do here is a well-known procedure. That's we do some transformation into time domain, and then we convolute this transformation over our velocity domain. So this is kind of a standard procedure, and Norwegian has a lot of experience in offshore industry. So this is kind of a state of the art how these effects are solved, and I believe this was being back there implemented quite good. So we provided an interface that it's able to calculate the convolution, where the properties itself are calculated externally. What's also maybe interesting to see here are these procedures, the equations that you see here. So either if you're not familiar with them, this is actually a standard procedure when you have a frequency-independent force and you like to transform it into a Newmark scheme or any other integration scheme. It's standard procedure that you first do an inverse Fourier transformation, where you transform the signal into time, and then you do a convolution. And this is somehow also similar for the wind. That's why I'm presenting those equations here, and you will see them a few times across the presentation. We will be focusing today on the wind buffeting formulation. This has been also developed due to my implementation in the software. We added homogeneous, actually linear wind field simulation, where we simulate the turbulent load on the bridge, and we also take into consideration the aerodynamic damping and stiffness. What's important for this is that we get first the input about the turbulent wind loads. I can only reference to some of my previous presented researchers. So they're trying to fill in those gaps, what to take the input values for the design of those bridges. At the same time, the input is also our dynamic performance. That means we have to somehow measure the aerodynamic properties, either with wind tunnel, or as you can see here, it's also possible to measure them with the CFD tools. And then once we have the input, we have to pick up a focus, what we would like to calculate. In general, we can superimpose the wind effects into mean wind, which is constant over time, buffeting, and vortex shadowing. As well, flexible structure tend to move in the wind, so therefore we have aerodynamic damping and stiffness. So we'll be talking today more about this aeroelastic effects, how to improve this formulation of the aerodynamic damping and stiffness. And this is the focus, and we can start by presenting a quasi-steady state wind load formulation, and this is current state of art in the TLP designs or any floating bridge design. Some of the software have this theory implemented. It's a good theory, and it actually works quite well. And I'm trying to present here in this slide what is the main focus here. Is presenting a wind load in a manner that we assume that this angle of wind attack is kind of fixed, and that flow around the deck is fully developed. And this is, of course, a rough assumption that it's not always valid. We see, or when we measure those forces and when we move the object, for very slow movement, this assumption is perhaps true, but when we have high oscillation of the deck, we are getting away from this formulation. So therefore, usually we can predict those damping and stiffness terms with the flutter derivatives, which are frequency dependent. In case of quasi-steady state formulation, these are constant matrices and are simply multiplied with velocity and respectively with displacement. What you can also see that there are a lot of zeros in these formulations here, and this is of course not good. When you measure the forces, the aerodynamic forces on the moving objects, those matrices get full, and that's why this theory lacks on the accuracy. As well as not suitable to predict any aeroelastic coupled flutter phenomena and etc. But it's a good starting point for investigating of wind buffeting effects, for example. So as well, my past work was involved in generating those turbulent wind field and project them to a bridge. We made a special solution that enables us to calculate wind field independently from the bridge structure. This is specially designed for this extra long suspension bridges or any other bridges to reduce the number of nodes. We have here maybe 40,000 final element nodes, and we are able to reduce this to 1,000 wind nodes, where we actually calculate the wind field, which is then projected to a bridge. This saves a lot of time, and also our algorithm to calculate the displacements, to calculate the turbulence intensities, was specially designed for this performance. And I must say this was a very good collaboration between NTNU and at that time also Bentley. And we did an efficient algorithm that works for this extra large bridges. And you can see here on the right-hand side, there are some input spectra that we are trying to simulate in the time domain. And just to check, we can then transform these time domain signals back into frequency domain. And in average, we should get the same curve. And this is somehow numerically matching, as you can see. And then I'll also maybe present a numerical example where this theory can be used. We have several different possibilities on how to cross those fjords. So this is one of the concepts I've been working past years. And that means we have here hydrodynamic effects, we have wind effects, we have current effects, as well we have all the loads. This we call it fully coupled nonlinear time domain analysis. So where technically all these effects are present, and I'll be showing here some of the result of those analysis from the past projects. What we can here, for example, extract is the deck movement and the deck displacements along the deck, which is about 5 kilometers long. You see here we have a frequency axis, which actually tells us which frequencies are excited, and also from the shape of this hills, technically you see which mode shape it is, and sometimes and in the middle. And what you can see here in the lateral direction, we have a huge response for the first mode. We measure those responses will be about 12 meters for some 30 to 40 meters per second wind. So these are quite large displacements, and as well we have a lot of... Yes.
It seems that your presentation has fallen out. Could you restart the sharing of your desktop?
Sure, yes.
Perfect. Now we see it again. Thank you.
Perfect. Yes, so we see here that the lateral displacement is rather large for the first few frequencies. And then we have this lateral movement, which is non-typical for suspension bridges. So this might be an effect that our formulation should be able to catch properly. As well, very interesting is the vertical response, where we have a wider frequency range, which is excitated. So we have a lot of modes with similar response participating. That means that if our load model is somehow frequency independent, then for sure this is the argument that we have to kind of use the frequency independent load model to capture all these frequencies properly. Otherwise, with the quasi-steady assumption, we are just technically picking up one frequency and assuming that this is the same for all of them. So this is kind of argument that goes with implementing more sophisticated wind model. Then in the next slide, we can see also some results of the model analysis where we plotted different damping. So these structures are relatively low damped structures, and it's very important. Any damping we can get on those structures, it's most welcome, so to say. What we found out that hydrodynamic damping has somehow limited range from 0.5 to 1 hertz, where actually all the interaction is happening regarding the hydrodynamic damping. But the aerodynamic damping is somehow all over the whole frequency range, and it's very important for our response. We can have also structural damping, which is, as I mentioned, relatively low for those structures. So we actually sometimes rely on the wind damping. And this is kind of an interesting phenomena. If we have a scenario, a combination that you have no wind and maybe some swell loading, you can get quite big excitation of the bridge because you don't have the damping there for the vertical modes. And this was observed during this work. On the right-hand side, we can split this aerodynamic damping into vertical mode and into the lateral mode. So the lateral mode is here presented with the red color, and you see there is it's less damped than the vertical modes, and the vertical modes are actually producing or adding more damping to the structure. That's also an argument why it's good to have those vertical modes described as accurate as possible. And so one last slide from the project work we did. Once all these features are, let's say, implemented across different softwares, and when we use one software to run it, it's really hard to get overview of the things. So what we did there is we made a manager that is able to you're just able in Excel to put the code, and then you run it in the background. And this was really helpful because we could now just simply input in Excel different combinations we want, and we will run them in the parallel in the background on our computer or on a server or etc. And it has a very clear hierarchy how the data is then stored. So this has been used for the different software inputs, but in background, the time domain was always run with the RM bridge. But it was kind of a flexible program that can be perhaps also extended to research use or other project use, and it serves as a kind of a platform to communicate with based on the results that we calculate. So we have to calculate at least 100 of combinations of wind, sea swell, and currents, so we can get quite quickly lost in those amount of data. So we developed a special naming system that, for example, C stands for wind, and then 4 stands for different return periods. In case of 4 is this 100 years return period of the wind. And then we have angle of attack, which is 90 degrees. And then we can also, in last 2 digits, we can present some other parameters as well. So somebody who is checking those results, he can immediately see what kind of event was there calculating. And this is really helpful for orientation and how to be able to extract the actual design values. But it's very flexible, and you can use it also for other codes to run. So at this point, I'm going to make a short break and make a preview of all the things that we have done so far. The first thing I will start is the bridge response, which was calculated with Newmark. I believe this was successfully solved. We were able to reproduce all the effects that we wanted in the software. As well, all the swell and wave loads and current loads, they have been correctly introduced into our scheme. Radiation, interaction, damping properties have been correctly introduced. We provided an interface that uses external provided data. And as I'm not an expert on hydrodynamic, so I just give them a 5-star rating. So if somebody doesn't agree, this is more of thinking of the calculation procedure rather than engineering practice. But here on the wind load side, I've been more familiar with the theory. I can comment that what we implemented is very good. The quasi-steady theory of wind buffeting load is sufficiently producing the response. However, we didn't include, for example, admittance functions, and those could be important. They could reduce the effect of buffeting, and that means cheaper design. So if I would be investor, I could like invest in those in this area. It would be also interesting to know what happens when we change the wind interaction formulation. And this is actually my focus on this research now that I'll present to you, is to improve this interaction formulation. And there are actually two good arguments. The ultimate limit state can be just predicted with frequency-independent self-excited force model. And the another reason is also the low wind response is better predicted with those models. That means all fatigue design and all other aspects of designing of the bridge are more correctly predicted. So that means that's also a cheaper design of the bridge. So this will be a focus of my next part of the presentation, where I was performing the research. And the basic idea was to have those formulation available in the existing framework. So what we did so far for the project. And so I came up with the idea how to join the project and the research work by introducing this formulation into available in some software. What we decided to do is we make a simple study. If this is possible, it's possible to on a simple case to have those formulation available for this framework of floating bridges. We started with an idea that we should develop, at least if it's possible, we should develop something that is rather simple to use, but we don't make any compromises on the accuracy. So that was kind of my wish. And yes, let's make first an overview of self-excited formulation, what this is. These are frequency-dependent forces due to the movement of the deck or any other object in the airflow. They are commonly described as flutter derivatives, which are also normalized frequency-dependent values. And usually these are 3 degrees of freedom, so we need about 18 derivatives to describe damping and stiffness terms. And what you see here in this slide is we can write this with a transfer function, where we simply this transfer function is a Fourier transformant in the frequency domain, and we can write this vector in the frequency domain as presented here. And our goal is, of course, to introduce this into time domain formulation. But they are commonly measured in frequency domain, so this is kind of a common presentation of them. So there are different methods already available in the research. One of them is rational transfer functions that been fitted to those derivatives, and then we find some analytical transformation for those expressions. So I took this theory. There are also others similar. They all work on the same concept, but they can be different aspects of it. What is common for all of them, that they have somehow there is a proposed equation that is fitted to the data, and this equation has to be analytically derivative. So that's the basic idea. We fit the data and then we make analytical transformation into time domain. And as you can see here, for the damping and for the stiffness, this could look something similar than showed below. Also, we have here infinite contribution and variation contribution. So on the next slide, we show how these functions can be fitted to numerical data, and this has been done on the on one of the aerodynamic cross-section, and these are fairly complex expressions, and they require nonlinear regression fitting. This nonlinear regression fitting is rather complicated for the practical use, so that's one of the reasons why this is not a common theory introduced in the commercial softwares, because even if you are able to have a code that does this automatically, you still need somehow a user control over some parameters or some experience on this topic. So this is one of the reasons why it's not widely used, and it's more in research areas. And we will now like to introduce this into our work. Generally, what we're trying to do here is we're trying to make a time domain a representation of forces which are a result of a moving object into the wind flow. On the right side, you see a small numerical simulation where this is directly calculated with the help of the CFD tools. And you see how the forces or how the pressure changes when the object is moving in the wind flow. So this is, of course, very interesting research simulation. But however, for some practical applications, this will be, I think at this point in time, impossible to calculate it for so many objects on the bridge. So therefore, we describe this motion with the frequency-dependent properties, and then with the right theory, we convert this into a Newmark scheme, and this is something that it's more practical for our application. And what we do here is, in fact, the same as we did in hydrodynamic. We are transferring our transfer function with inverse Fourier transformation, and this is then mapped into a displacement domain via convolution integral below. So that's the background, and technically all theories or all fitting work in a similar principle. And we can make here an example of I call it traditional approach of rational functions. So you can find those in different papers where you see that we have a transfer function which is analytically, we analytically can find inverse transformation of it, and then we can convolute over that inverse transformation, and when we get an expression, and if we're able to build inside of the software this expression, then we have technically our self-excited formulation. What's also interesting to see, some of the properties, for instance, these first two terms, A1 and A2, are somehow presenting infinite contribution, in some sense the same as a quasi-steady contribution, and then we have also the part which is convoluted, and this presents the variation, the frequency variation, which we're trying to catch here properly. Well, the biggest challenge is if you're using commercial software that you don't have access to the code, and you're not able to program those effects inside. So we came to conclusion that this formulation is not really suitable for our framework, for existing framework where we calculated the response, and due to the lack of the access in the code. What we usually do, engineer, in those situations, we try to reformulate in the way that we are able to introduce it in the software. And this was the big question: are we able to introduce those effects? And so I came up in the contact with NTNU, and well, I asked them if something similar has been done before, so I don't have to, you know, do a whole PhD about it. And it was my lucky day. Nobody really did this before, so I was able to research those effects. And we came up with an idea that we can perhaps transform these equations of rational functions in a way that we are able to convolute it numerically over the velocities. And this has been already implemented as hydrodynamic damping. And in this case, we just have to present this as aerodynamic damping in the proper final element format. So that was the main idea, actually came out of the hydrodynamics, and we like to reformulate the equations in a way that we are able to include them in our current scheme. What we had to do, we had to pretty much rewrite the whole rational functions, and we did this in 2 steps. You see here the end results of this reformulation that will be in detail explained in the PhD. We did this in a way that we first changed the convolution integral, where we convolute over velocities instead of the displacement. We came up with the expression presented here, and this expression actually convolutes here. You can see at the end we convolute over velocities instead of the displacements. If you compare to previously presented, it's a little bit shorter, so maybe that's why it's maybe also could be used for some implementation in Newmark. But it produced exactly the same result as previously presented. We named this one self-excited force model 2, so that we are later able to compare them. And the original one is self-excited force model 1. In the second step, we have to somehow be able to reproduce this frequency dependency in a hydrodynamic way. So what we have to do is we have to modify this transformation. Instead of having analytical transformation, we have to do it numerically. And this is possible. So we can present the frequency dependency in the form of a table. So we are not obliged anymore to use analytical transformation, but we can reformulate this in the form of table. And that's, I think, also a good argument that it's easier to work with those tables as engineer than work with those complex and rather difficult to understand expressions. So this has been done, and this self-excited force model 3 actually show that we have reformulated the rational functions, and this kind of format is now a candidate which could be implemented in the software. So we already have access to the hydrodynamic interface that has the same functionality, plus we have some quasi-static contribution that we also have to take care inside of the software. So this is what we came up, and the best way to prove this is to make a benchmark testing, and we did here 3 degrees of freedom, drag, lift, and moment, harmonic movements, and this is superposition of 70 random frequencies. For this script, we always choose random generated parameters as velocity, width, amplitudes, natural frequencies of these motions, and phases, and etc. So each time we run, we get a new signal, and based on rerunning this a few times, we can get pretty good idea. If they always match, then our theory works. And this also proves that the developed model, they are sufficiently, they are producing numerically exactly the same result. So we are now able, with help of some numerical tools and theory, to rewrite this equation in the format that we are able to introduce inside of the software, which is great. This is actually a goal of the research, and we did not know at the beginning if this was possible, but this actually proves that this is possible. Yeah, so that's great, right? So we kind of achieved one of the goals, but also we have done a lot of work on how to develop this formulation, and we came up with some very interesting ideas, and that's following that we are able to actually now have this interpolation done with polynomials. So since we are not using any analytical transformations, we are able to use the polynomials because we are numerically transformed, and we can use any other interpolation function for that matter. And this really helps since we don't have to use the anymore the interpolation between real and imaginary part, and it kind of removes the nonlinear regression procedures, which is great. And why is this so? Because we proved that there is a valid relation between damping terms and stiffness terms, and this is presented here in this above equation. And this relation it's mathematically proved, but we also prove it on the real data. And we are now able to do following. We can interpolate, or we can fit the data only to damping or only to stiffness terms. So this was previously not possible. We have to kind of make a fit to both of them. But since this relation has been proved, it's possible to really fit the data to either damping or the stiffness. And that means if we're fitting to a stiffness part, then we are making convolution over the displacement. And for variation part, if we're fitting to the damping, we just simply do convolution over velocities. Plus, we have to take care of the quasi-steady part, as everywhere. That was really improvement, and this is a big step towards simplifying the theory, and that it's maybe more reasonable to use in some practical applications. So that was somehow a side result of our research. And this is again a benchmark test on the vertical degree of freedom motion, where we use this rational functions, this standard fitted to both sets of data, and then we use a simple second order polynomial fit in a self-excited force model 4. And the green one is then fitted to a damping part, and we convolute over the velocity. So they are all producing the same results. Of course, I picked up example where you can see a small differences, and these are due to the different fits, because we use here polynomials, and the rational functions have a different shape of the fit. But you can see that this theory really works, and this is a numerical proof for that. So this has been focused on the research to introduce those formulations. And now we came up to further benchmark testing, where we can find some candidates where this new formulation can be used. So for one, there have been several software used for those projects. I've been working a lot with RMBridge. So in my thesis, I'll also present a benchmark in the RMBridge, how this self-excited formulation is working there. But there are also other bridge softwares that are candidates. Sophistic has also a very good wind solution. We also, my group also used OrcaFlex for some hydrodynamic simulations and time domain integrations. So OrcaFlex already has all the hydrodynamic implementation, plus it has a possibility to convolute over the velocities. So it's a perfect candidate, for example, for this theory. As well, others, ANSYS and Abacus, of course, they already have access there where you can program your own code. So they are definitely candidates, and it's possible to use it there. As well, other softwares, research softwares, perhaps this new formulation, it definitely shows some advantages to be used because it does not require so much work on the nonlinear fitting, and perhaps the implementation it's somehow more convenient. And so these are all the candidates, and the results of the tests will be then presented defended in my thesis. I also came here to some conclusion. My goal was to have a decent overview of all dynamic loading on the floating bridges. And as I briefly present you here, we have successfully introduced different formulations, hydrodynamic, wind, currents, and all this in a new mark time integration scheme. Plus, we developed a new formulation of self-excited forces, which is now being tested and being used for commercial software use. Some of the softwares, it's possible to use it there, and of course use it on our floating bridge projects. What also brings us is that we have simplified the theory by a lot, because we have now a simple linear regression. It's more easier to use, in my opinion, this theory. It's more engineering way of thinking. Instead of having this complex formulas, you just have to, as engineer, you have to prepare a damping table which presents your flutter derivatives. And it's kind of easier to understand if you have this frequency dependent damping, and this is your input for the analysis. We have improved efficiency. I don't know if you noticed, but we somehow removed the sum of all the convolutions. So in our classical rational functions, there are a few convolutions that needs to be evaluated and summed together. We now, with the numerical approach, we just do one convolution. So that's more computationally efficient. And this is of course good for those time simulations which are very long. And also this theory, I think, in my opinion, is a big money saving for all the projects. That's because of the two reasons. The first reason is we are now able to do accurate and decent ultimate limit states calculations, which were previously not possible with quasi-steady theory, and they are embedded in already existing framework. So it's very accurate as far as it goes for the floating bridge. And as well, we have more accurate serviceability limit states, and these are also important for fatigue design and some other aspects. So the bridges with those theory will be definitely built economically. So these are kind of reflected effects of our work here on actual projects. Yes, and this is what I wanted to show you today. I hope I am right on time, and please, you're welcome to ask me questions. In case you're watching the video, you can write me an email and get in contact.
Thank you so much for your presentation, Mitja. I really enjoyed it. And as Mitja now said, we'll open up for any questions. You can also write your questions as a direct message, and I'll read it up for the video. Well, Cheshire just announces that it's good to hear that we can save money on your research. And I'm also very glad of that.
Yeah, so I think this is a purpose of research. Research in the industry, that means you can save money. I think that's a good result of the work of different groups together. Yeah.
Yeah. When do you see that you'll be finished with your this part of your research?
So far the theory has been developed. We have shown on the small examples that this theory is valid and has been validated. The work in progress at the moment is validated inside of commercial software, and this is kind of under work at the moment. I didn't show some of the results because this is really extensive work. You have to check for accuracy and for how robust is this implementation. But this shows that end of the summer we should have those, at least for one candidate, we'll have this end of the summer, those tests available. Yeah.
Perfect.
Yeah. Hi, Matthias. This is Jungao. Can I ask several questions?
Sure.
Yeah.
Yes.
Thanks for your very nice presentation. I'm Jungao from University of Stavanger, and I have maybe 3 small questions for you. So the first one is, I saw you in one of the slides, I don't remember the number, but you presented both the lateral and the vertical response, the spectrum in the 3D contour plot. And it seems to me that for the vertical motion, it's not the lowest frequency which is dominant, but it's several more higher frequency. But can you show to?
I'll try to go back perhaps to this slide.
Not yet. The one with 3D contour plots, where you show the spectrum for yeah, this one, yes. So for the vertical response, it's not the the lowest mode which is dominant for vertical, right? What you show in the result.
Yes, that's correct. Yeah, it's not the lowest mode that it's having the largest amplitudes. It's somewhere in between. Yeah.
Yeah,
that's
but
correct.
then to me, because for a TLP supported floating bridge, if you look into your mode, like the fundamental mode, the first mode, the global mode, you actually have a contribution. I mean, how to say? You have a vertical component accompanied by the main or dominant horizontal mode, isn't it? Because when imagine your TLP is moving sideways in the lateral direction, it will be dragged down. It's called the set down in hydrodynamic sort of term. So you should have do you have some comment on that? Because if you have a very large contribution in the lowest mode for your horizontal mode, you should also have a relatively big contribution in vertical direction, right? Because this is what we found from Abacus simulation.
Yeah. So you're saying that this lateral mode and the vertical modes are somehow combined due to the large lateral motion?
Yes.
I definitely agree with that, and I think this is one of the main reasons why we were in the first place trying to do a nonlinear time domain simulations, that those coupling effects and nonlinear effects could be observed there. So since we are doing this in the time domain, and each time step we are calculating the larger displacement equations, those effects of the larger displacement could be present. I'm not sure to answer that if it's present for this, because I was not focusing on this.
Okay.
But I just present the results as they are, and they are based on the nonlinear structure analysis and all the interactions there. Yes.
Yeah, okay. So the second question will be about the computational time, because you mentioned you're actually using convolutional integrals to account for the aerodynamic derivative terms in aerodynamic part. So how long does it take for one simulation, for example, for your implementation?
Yes. So this is actually currently being tested. This is one of the tests where you put all these convolutions on your bridge. You have to be careful what happens with your computational time.
Yeah.
I have so far I can say I expected to be more computationally demanding, but it's really not, because we have a very effective algorithm inside of the software that's able to calculate this convolution very effectively. It's not the most expensive part. It's not actually the convolution itself, but it's repeating the convolution 30, 40, 50 times, because inside of the one-time step, we have to repeat it 40 times. And we did this by splitting those convolution integrals in two areas. One area is everything what happens before and then save it into a value, and then we just calculate the small area that is changing inside of the new mark. And I think this greatly improves up to 50 times the efficiency of this algorithm. And once you put all these convolutions, for example, for the deck, I think the deck is here the main actor, and this is where you should put those formulation. It's not really that big. We can talk about 30 to 50% more computational time. So far, we have about 25 hours on one core on 4 gigahertz computer to run this time domain simulation of about 1 hour. So we expect here some increase, but it's not going to be that dramatic, I believe.
Yes, great, thanks. One last thing is, in one of the slides, you also mentioned you were simulating non-homogeneous wind field, right? And can you explain a little bit about that, if you have some time left?
Let me find it. Just a second. I'll just first find the slide, so it's easier to see for the audience. Yeah, I think I found the slide here. So this is the general presentation of what we're doing here is creating these turbulences, which is then projected to a bridge. And during this calculation of the turbulence, you can either assume that this is somehow homogeneous over the whole bridge and over the height, which is not really a realistic assumption, so to say. This turbulence intensity depends on the height and depends on the mean wind velocity. So we are trying to simulate this as well. So this is kind of a side solution. It's really hard to do a non-homogeneous simulation on this large bridge. We have like a lot of numerical problems, but we have found a good way around that. By simply splitting the mean wind, which is like logarithmically distributed, and then we calculate the turbulence intensity, which is based on homogeneous wind field for some reference height, for example, for the deck, which is the most relevant participant. And then what we do, we can like modify this turbulence intensity for the factor that should be modeled. So you can kind of use a hybrid method where you calculate it homogeneously because of the numerical problems, and then you try to match the actual non-homogeneous result. So that was one of the idea, and that's up to user to decide. Usually we run into some Cholesky decomposition, and it's not possible. I've been working for this 3 months, and it's really sometimes hard to make sure that the composition works, and that's why we like to have it as homogeneous as possible. But as engineer, we like to have it non-homogeneous. Of course, these are then design values, so you have to kind of find a balance, I guess.
Yeah. Okay. Thanks. Yes.
Yeah. Thank you for questions. Okay.
Thank you. Are there any other questions? I think we have time for one more. Well, if there's no more questions, as Mitja said, if you think of something later, just send him an email. Once again, thank you so much for the nice presentation you had for us. I really enjoyed it. I hope other people did as well. We'll make this video available through our website, and I will stop recording now.